Hello there, and welcome back to Once Upon a Lecture. I'm Princess Aurora, and say, wait a minute, have we met before? I think we have. That's right, once upon a dream. Do you remember the dream where we talked all about a two-way ANOVA? Well, if not, you're in luck because I'm going to tell you all about it right now. Oh, but I must warn you, if you have not yet watched my godmother's lecture on the one-way ANOVA, this one will probably be a bit confusing. So please make sure that you watch the lecture by Maleficent on a one-way ANOVA first before you come and join me to learn about two-way ANOVA. Let's take a look at some of the topics we'll be discussing. So the first thing we'll do is we'll talk about what is a two-way ANOVA and how does it differ from a one-way ANOVA. We're also going to learn how to find significance when it comes to calculating a two-way ANOVA. So while this is going to be similar to the way we did it for a one-way ANOVA, now because we have two independent variables, it's going to just be a bit more extensive. Now also, if you recall, when we were learning about calculations for one-way ANOVAs, what we did to organize our data and our numbers is put those numbers into an ANOVA source table. So what we're going to do is learn about how the ANOVA source table for a two-way ANOVA differs from the source table from a one-way ANOVA. And lastly, as usual, we'll talk about a couple examples in which we will apply a two-way ANOVA for hypothesis testing. All right, let's get started. So what is a two-way ANOVA? Well, if you remember, ANOVA is an acronym for Analysis of Variance. Previously, we learned how to calculate a one-way ANOVA, and a one-way ANOVA is used when a researcher is testing more than two levels of one independent variable. When we talk about a two-way ANOVA, it means we are going to have two independent variables. So one-way ANOVA, one independent variable, two-way ANOVA, two independent variables. Another word for a two-way ANOVA is a factorial design. Now, if you remember, the minimum number of levels a variable must have is 2. So therefore, if we have two independent variables, we're going to have a minimum of 2 levels for one variable and 2 levels for another, which would give us a minimum of 4 different combinations of levels to compare. This design allows us to test multiple variables at the same time, and it also increases our power by reducing the number of subjects needed for these tests. So for example, if you think about conducting a research experiment, we know that the larger our sample size, the stronger and more powerful our experiment will be. If you have a two-way ANOVA, it's almost like doing 2 separate one-way ANOVAs, but instead of recruiting different participants for each one, you basically test more than one variable for the same group of people. So that is how we can increase our power by using the same participants to test more than one variable. A factorial design is also used when you have more than 2 levels for multiple variables. Factor is another word for levels of a variable. So when I say factor or I say levels of a variable, those two terms will be used interchangeably. If a variable has 2 levels, that is the same thing as saying that it has 2 factors. Each level is equal to 1 factor. And all these factors have to share a relationship. Hence, we call it a factorial design. But what we also could do with the two-way ANOVA is examine interactions of different manipulations of these 2 variables. Interaction of variables is actually very, very common. If you think about it, human behavior is rarely influenced only by one intervention or one independent variable or treatment effect. So because in the real world we can see that things combine together to produce effects on human behavior, that's why we created an analysis called a two-way ANOVA so that we're able to measure more than one variable at the same time. What's important to understand is that even though you have 2 independent variables, and an interaction or a combination between the 2 is possible, what is also possible is that each variable alone can have a unique effect on the dependent variable. So for example, I was recently walking through the forest and I found an injured squirrel. I want to nurse it back to health, but my new furry friend just doesn't want to eat. I tried to think of certain factors that I could manipulate, in other words, things I could try to get him to eat. The first thing I thought was, perhaps the portion I was giving him was not appropriate. So I decided to experiment with small, medium, and large size portions. Then I thought to try different types of food. So I also experimented with nuts, berries, and a combination of the two. Using hypothesis testing, I want to determine whether either of these will change the squirrel's eating habits. So if we dissect this a bit further, we can see that the first factor or variable I experimented with was the size of the portion. So we're going to go ahead and call this variable A. If I ask myself how many levels does this factor have, I'm going to say 3, because I have 3 different types of sizes of portion. I have small portion, medium portion, and large portion. The second factor, which we'll call variable B, I experimented with was the type of food. And if I think about how many levels that one has, that one also has 3 levels because I gave the squirrel berries, nuts, and a combination of berries and nuts. So what type of design do I have? Well, because I have more than one independent variable, in this case I actually have 2, and each variable has more than 2 levels, I will be using a factorial design or a two-way ANOVA to analyze the answer to this question. So how many independent variables do I have? What are they? And how many levels does each variable have? Well, I know that I have 2 independent variables. The first one is the size of the portion, and the second one is the type of food. The size of portion variable has 3 levels, small, medium, and large. And the type of food also has 3 levels. So if I consider the levels of one variable by the levels of the other variable, I would call that a 3 by 3 design. So again, the first blank is going to be filled by the number of levels of the first independent variable, which is 3. And the second blank is going to be filled by the number of the levels of the second independent variable, which is also 3. So in this case, I have a 3 by 3 factorial design. And this basically means because 3 times 3 is 9, it means I can have 9 possible combinations of effects with these 2 variables. So what that means, for example, is if I pair a small size portion with nuts, I can also pair a small size portion with berries and a small size portion with a combination of nuts and berries. Then I can do the same thing with the medium size portion. I'll pair a medium size portion of berries, a medium size portion of nuts, and a medium size portion of nuts and berries. And then I'll have to do the same thing with the large size portion. I'll have a combination of a large size portion of berries, a large size portion of nuts, and a large size portion of a combination of berries and nuts. So I have 3 possible combinations for small, medium, and large in correspondence with the type of food, leaving me with 9 possible paired comparisons. However, each independent variable on its own can also have an effect on our dependent variable, which in this case is the squirrel's eating habits. So if an independent variable alone has an effect on the dependent variable, we call that a main effect. Because we have 2 independent variables, we can have 2 possible main effects. In other words, however many independent variables you have, it's going to equal the number of possible main effects you can have in the analysis. I have 1 main effect for variable A, and I have 1 main effect for variable B. Remember, variable A was the size of the portion, and variable B was the type of food. So each main effect is a one-way ANOVA in and of itself. So in other words, when we are running a two-way ANOVA, we are checking to see if the independent variable, for example, size of portion, has a significant effect on the squirrel's eating habits. I'm also in the same analysis running a separate one-way ANOVA to see if the type of food I'm giving the squirrel is going to have any effect on the squirrel's eating habits. So those are the 2 main effects. If the size of the portion alone improves the squirrel's eating habits, then I have a main effect of variable A. If the type of food alone improves the squirrel's eating habits, then I have a main effect of variable B. But it is also possible that a specific combination of the size of the portion with the type of food will actually improve the squirrel's eating habits. In that case, I would have what is called an interaction effect, an interaction of variable A in tandem with variable B. And the way we say this is an interaction effect of A by B. So when you see the little X, it's kind of like a multiplication symbol, and we use the word by to complete that sentence. So once again, if I have an interaction effect, that means that there's a specific level of the first variable and a specific level of the second variable that when paired together are going to change the squirrel's eating habits. So an interaction effect shows the joint effect of the two independent variables. In other words, the two factors or variables have to work together to produce an effect on the dependent variable. For example, perhaps the size of the portion alone had no effect and the type of food alone had no effect. But when combining a specific type of food with the specific size of the portion, the squirrel will actually begin to eat. So in other words, in an interaction effect, the effect of one factor depends on the level of another. Now let's talk about finding significance of a two-way ANOVA. When testing hypotheses, researchers always use the 7 steps of hypothesis testing. So for testing factorial designs, we're going to use the same 7 steps. However, when we were conducting one-way ANOVAs, we compared our F computed value to a critical F value, which we found using a special table known as the critical values of F table. For two-way ANOVA, we're going to compute 3 F values and compare them to 3 F critical values. So why do we have to do it 3 times? Well, remember, each effect requires its own F test and its own decision about the null hypothesis. So where are these 3 effects coming from? Well, we know we have 2 main effects because we have 2 independent variables and we have 1 possible interaction effect of those 2 variables. So 2 main effects plus 1 interaction gives us a total of 3 possible effects. Each effect, each variable is going to have its own hypothesis. So if each comparison has its own hypothesis, that means I'm also going to have to make 3 different decisions about these hypotheses. So I'm going to have a null hypothesis for the first independent variable, the main effect of variable A, which was the size of portion. Then I'm going to have a separate null hypothesis for the main effect of variable B, which was the type of food. And then lastly, I'm going to have a null hypothesis for the interaction of the 2 variables. So I have 3 different effects, 3 different F computed values, 3 F critical values, ultimately to lead to 3 different decisions about the null. So how do we actually calculate F? Well, the way we do this is by a series of different division ratios in our ANOVA source table. So let's take a look at the ANOVA source table for a two-way ANOVA. So some of this may look familiar and some of this may not. Let's take it line by line and discuss what we see here. So the first row is the between group variance. Again, this is going to tell us how the groups differ across the different conditions of the independent variable. However, because we now have 2 separate independent variables, that first line of between group variance is essentially separated into IV1 and IV2 variances that we see directly below that. Further below that, we have A by B as a source, which is going to be our interaction effect. So essentially, if you were to add variance for IV1 plus variance for IV2 and variance for the interaction, that would all make up our between group variance. Within group or error variance is the same as it was in the one-way ANOVA, which is going to be the variance that tells us that factors in individual differences as well as experimental error. And total variance is essentially the sum of all of the things prior in those columns. So what's important to understand is that when we talk about a two-way ANOVA, when we're talking about the source table for a two-way ANOVA, the things that are now different are we've separated the between group variance into three separate variances. We have variance of independent variable 1, which is the size of the portion, variance of independent variable 2, which is the type of food, and then the variance of the interaction of those two variables, which is illustrated by A by B. So as you can see, the degrees of freedom for each of these are similar to the way we've been calculating between group variance before. So if we talk about the levels of A minus 1, because we had three different levels of variable 1 of the size of the portion, small, medium, and large, 3 minus 1 would give us 2. For the levels of independent variable B, or independent variable 2, which was the type of food, we had three levels of that, nuts, berries, and a combination of the two. So 3 minus 1 would also give us 2. And then the interaction degrees of freedom are going to be A minus 1 times B minus 1, which we've just calculated is 2 in each of those. So 2 times 2 would give you degrees of freedom of 4. And as you continue moving to the right through the source table, you can see that everything else stays the same. The way that you locate mean squared is by dividing sum of squares by degrees of freedom. And then the way we actually calculate F computed for each effect, if you pay attention, it says mean squared of variable A divided by mean squared within. Then if I want to find F computed for variable B, I'm going to do mean squared between, again, divided by mean squared within. And lastly, for the interaction, I'm going to do mean squared of A by B divided by mean squared within. So the error variance, the mean squared within, is the denominator for all of the F computed ratios. What does change is the numerator, okay? So make sure that you don't get those confused when you calculate these on your own. The numerator corresponds with the type of variance you're talking about, the type of independent variable, but the denominator will always be mean squared within. All right? So why don't we try an example together so that we can actually see how the numbers are applied to these new calculations we just learned about. Aurora, that's me, is interested in the effects of pet type and pet gender on the happiness level of their owners as measured by the subjective happiness scale. She realizes that she and her friends who have birds feel different about life than her friends who have squirrels and those who have bunnies. Additionally, Aurora assumes that perhaps the gender of their pets also contributes to their owner's level of happiness. She runs her test on 90 people, with 30 people in each condition of IV1 and an even number of male and female pets in each category. Use the 7 steps of hypothesis testing to determine if pet type and pet gender have an effect on their owner's level of happiness. So before we get started, what we really need to do is understand what type of analysis should we be using to answer this question. If you thought to yourself a two-way ANOVA, you're absolutely right. But I want to know why. So we use a two-way ANOVA when we have two independent variables. So that brings me to my next question. How many independent variables do we have? And what are they? Well, it looks like we have two independent variables. The first one is pet type, and the second one is pet gender. So how many levels does each independent variable have? Well, I know that pet type has 3 levels. We have birds, squirrels, and bunnies. And pet gender is broken down into 2 levels as male pets and female pets. So if we want to fill in the levels of the factors into this equation, we would say that this is a 3 by 2 design. 3 levels of variable 1 go in the first line, and the 2 levels of variable 2 go in the second line. Because I have 3 levels of pet type and 2 levels of pet gender, this gives me a 3 by 2 factorial design, which means that I have 6 possible combinations of effects between IV1 and IV2. How many F tests will we conduct? Well, we just discussed the fact that we can have a main effect for each independent variable, and we can also have an interaction effect for the 2. So that looks like I'm going to have to do 3 different F-tests. 2 for the main effects of pet gender and pet type individually, and then 1 possible interaction effect combining the 2 together. State a null and alternative hypothesis for each F-test. All right, so this is where things might get a little bit tricky, but don't panic. All you have to do is think of a sentence for each possible effect. So if I have 3 possible effects, it means I'm going to have 3 different null hypotheses, and I'm also going to have 3 different alternative hypotheses. Let's start with the first variable. My first variable is pet type. And remember, my dependent variable is the level of happiness of the pet's owner. So stating a null hypothesis would be indicating that there is no difference between the type of pets a person has on their level of happiness. So the null hypothesis would be there is no significant difference in an owner's level of happiness depending on if they own a bird, a bunny, or a squirrel. In other words, the type of pet someone has does not affect their level of happiness. The alternative hypothesis for this particular effect would be the exact opposite. So the alternative hypothesis would be that pet type does have a significant effect on the level of happiness of an owner. Owning a bird, squirrel, or a bunny actually will change the owner's level of happiness. So that's the null and alternative for main effect 1, pet type. Now we have to do the same thing for pet gender. The null hypothesis for pet gender would be there is no significant difference in an owner's level of happiness depending on the gender of their pet. The alternative would say the opposite, that there is a significant difference in the level of happiness of an owner depending on if their pet is male or female. And the last null and alternative set of hypotheses we have is for the interaction effect. So remember, the interaction effect combines both variables together, and it says that the 2 variables together will have an effect on our dependent variable. So the null hypothesis would say that the interaction of pet type and pet gender will not have a significant effect on an owner's level of happiness. And conversely, the alternative would say that the difference would exist. So the interaction or the combination of pet type and pet gender will have a significant effect on an owner's level of happiness. All right, so after collecting my data, here are the values that I come up with. I have sum of squares for pet type equal to 100. I have sum of squares for pet gender equal to 20. I have sum of squares error equal to 1200, and my total sum of squares is 1500. I also know that my degrees of freedom for the type of pet is 2, and my degrees of freedom for type of gender of the pet is 1. Altogether, I ran my experiment on 90 people, with 30 people in each condition for the type of pet. So what I need to do now is plug these values into my source table. So just as a reminder, this is what our two-way ANOVA source table looks like. If I put in the values that I already know, that I've calculated, I can see the sum of squares for pet type, sum of squares for pet gender, sum of squares within, and sum of squares total. It looks like what I am missing is the interaction sum of squares. So how can I find this interaction sum of squares? Well, if you remember, we did something very similar with the one-way ANOVA. Essentially, because I know my total sum of squares, all I need to do is subtract the values I have from the total. So this means I'm going to take 1500, subtract 1200, subtract 20, subtract 100, and ultimately I'm left with 180. So 180 is going to be my sum of squares for the interaction of pet type and pet gender. Let's move over to the degrees of freedom column. I know that degrees of freedom for variable 1 is 2, and degrees of freedom for variable 2 is 1. In other words, I had 3 levels of pet type, and 3 minus 1 is 2, and I had 2 levels of pet gender, and 2 minus 1 gives me 1. Now let's look at the degrees of freedom for the interaction effect. We have a minus 1 times b minus 1. We know that a minus 1 is equal to 2, and 2 minus 1 is equal to 1, so essentially I have 2 times 1 is going to give me degrees of freedom of 2 for my interaction degrees of freedom. Now let's take a look at the within variance degrees of freedom. That formula says total minus cells. We know that the total number of people we tested was 90, but what does cells mean? Well, if you remember the whole 3 by 2 factorial design, the 3 times 2 is basically what your cells are. It's the number of possible comparisons you can have. So essentially, cells are equal to the levels of A multiplied by the levels of B. If I had 3 levels for variable A for pet type, and I had 2 levels of variable B, pet gender, all I have to do is multiply 3 times 2. When I multiply 3 times 2, I get 6. So essentially, this is going to become 90 minus 6. The total N that I was given, the total number of people I ran my experiment on, was 90. 90 minus 6 is going to give me 84. So degrees of freedom for within group variance is going to be 84. And then lastly, for degrees of freedom total, that is just going to be N minus 1, as usual. N is going to be 90, minus 1 leaves me with 89. So now that we've completed this entire column, we're ready to calculate mean squared. Remember, mean squared is calculated by dividing sum of squares by degrees of freedom. So let's take the first row for independent variable 1, which is pet type. I'm going to divide the sum of squares of 100 by the degrees of freedom 2 to get my mean squared for IV1. I'm going to do the same thing for independent variable 2, which is pet gender. I'm going to divide sum of squares 20 by degrees of freedom 1. The next thing I'm going to do is find my mean squared for my interaction effect by dividing sum of squares 180 by degrees of freedom 2. And lastly, I need to get my mean squared error, which is going to be 1200 divided by 84. So once I've calculated my mean squared column, these are the values that I should be left with. The next thing I'm going to do is calculate my F computed value. And here is where we need to be extra careful. So remember, we're going to take the numerator of the corresponding independent variable or interaction effect, but the denominator will always be mean squared within. So if I look at mean squared of IV1, I can see that that is 50. I'm going to divide that by mean squared error, which is 14.29. And that is going to give me an F computed value of 3.50. If I do the same thing for independent variable 2, which is pet gender, I'm going to divide mean squared 20 by mean squared within 14.29. That is going to leave me with an F computed value of 1.40. Lastly, for the last effect I have is the interaction effect. I'm going to divide mean squared interaction, which is 90, by mean squared within, which is 14.29. I'm going to be left with an F computed value of 6.30. So once we've calculated our F computed, the next step is to compare this F computed value to our F critical value. So the F critical value typically comes from a chart. And in this chart, we are going to use our degrees of freedom for between and degrees of freedom within to find the critical value. But remember, because now you're going to do this 3 different times, it's really important that we make sure we're using the proper and appropriate degrees of freedom for each specific effect. Let's take a look at how to do that. So we know that we need to calculate 3 F tests. 1 for main effect of pet type, 1 for main effect of pet gender, and 1 for the interaction of the pet type and pet gender. So here is our critical values of F table. Again, we want to make sure that we use the appropriate degrees of freedom for each individual test. So let's talk about them separately. The degrees of freedom for pet type are degrees of freedom between 2 and degrees of freedom within 84. Then we have degrees of freedom for pet gender, which are different. Degrees of freedom between is going to be 1, and degrees of freedom within stays 84. And lastly, we have our interaction effect. Degrees of freedom between is 2, and degrees of freedom within are 84. So if you look at this chart, you can see that we don't have exactly 84 degrees of freedom. listed here, but we can see the number 60 and we can also see the number 120. So because 84 is closer to 60 than it is to 120, we're going to go ahead and use the critical values for degrees of freedom of 60. So similarly to how we did with one-way ANOVA, what we need to do is find our degrees of freedom between across the top and degrees of freedom within going vertically from up to down. So horizontally, we're going to put our finger on the number 2 for degrees of freedom between for pet type, and we're going to slide our finger all the way down to 60 to find our degrees of freedom within. We're going to do the same thing for degrees of freedom of pet gender, but this time we have degrees of freedom between equal to 1, and we're going to slide our finger down to 60. The last thing we're going to do is degrees of freedom for interaction, which if you see are exactly the same as degrees of freedom for pet type. So ultimately, this is what you are left with. A critical F value of 3.15 for pet type, a critical value of 4.00 for pet gender, and once again, critical value of 3.15 for the interaction. So these are our critical values that we're going to plug in here into our ANOVA source table. Once we do that, we're ready to start our 7 steps. Here we go. All right, so step 1 is to state all the possible null hypotheses. Let's go one variable at a time. So the first independent variable is the pet type, and we could say that pet type alone has no significant effect on an owner's level of happiness. Our second independent variable is pet gender. Pet gender alone has no significant effect on an owner's level of happiness. The last thing we have is our interaction. The combination of pet type and pet gender have no significant effect on an owner's level of happiness. Remember, the alternative hypotheses are exactly the opposite. So we have to state 3 alternative hypotheses because we've had 3 null hypotheses. So pet type alone has a significant effect on an owner's level of happiness. Pet gender alone has a significant effect on an owner's level of happiness. And lastly, the combination of pet type and pet gender has a significant effect on an owner's level of happiness. Whew. So step 3, as usual, is always going to be to set alpha to 0.05. Remember, this means that we're willing to accept only 5% chance of error and 95% confidence that our decision about these nulls is going to be correct. Step 4 is to set our rejection rule. Remember, we previously found 3 critical F values, 1 for each effect. Critical F for pet type is 3.15, critical F for pet gender is 4.0, and the critical F, once again, for interaction is going to be 3.15. Step 5 is to compute F. We've also computed 3 different F values for each effect. The computed value for pet type was 3.50. The computed F value for pet gender was 1.40. And the computed F value for our interaction was 6.30. So we know that step 6 is the time to make a decision for each effect. So if on the left-hand side we can see the type of effect, we have 2 main effects in one interaction. The table next to it are our computed F values, and then the third column shows us our critical F values. So what we need to do is make a decision for each effect. Remember, if the computed F value is greater than or equal to your critical F value, your decision will be to reject the null and thus to conclude that there is a significant difference based on that main effect. If your computed F value is less than your critical F value, then you would conclude that there are no differences and you would fail to reject the null. So let's take a look. For the main effect of pet type, is the computed F value of 3.50 greater than or less than our critical F value of 3.15? It looks like that one is larger, so we're going to reject null and conclude that pet type does have a significant effect on an owner's level of happiness. The second independent variable was pet gender. The computed F value there is 1.40. 1.40 looks like it's smaller than our rejection rule. It's smaller than our critical value of 4.0, so our decision there would be to fail to reject the null and conclude that there are no significant effects on levels of happiness based on pet gender. And the last comparison we have is our interaction effect. Our computed F value is 6.30, which is definitely larger than our critical F value of 3.15. So we're going to reject the null there as well. If we reject the null, once again, that means that we are concluding that there are differences or that the interaction effect does change the owner's level of happiness. Just as a reminder, whenever you're making these comparisons of computed F to critical F, you should always be taking the absolute value of the numbers. In this case, all of our numbers are positive, but even if they were negative, if any of your computed F values were negative, you would still have to consider them in their positive form when making the comparison to the critical value. All right, so that brings us to your favorite part, writing a good conclusion. When writing a conclusion for a two-way ANOVA, you still want to make sure that you include the F statistics at the end of your sentences, and you also want to make sure that you address every comparison, every effect. So if that means you're going to have 3 different sentences, then that's absolutely correct. You should have 1 sentence for each effect. So here's an example. A two-way ANOVA was conducted to test the effects of pet type, birds, squirrels, and bunnies, and pet gender, male or female, on their owner's level of happiness. The results showed a significant main effect of pet type, comma, F, capital F, lowercase f means frequency. I'm going to put a capital F and include the degrees of freedom for pet type. 2,84 is equal to my F computed value of 3.50. Because I rejected null in this particular effect, my p-value is going to be less than 0.05. So the results showed a significant main effect of pet type and a significant interaction effect of pet type and pet gender, comma, F, put in the degrees of freedom for the interaction, which is 2,84, is equal to our F computed value for the interaction, which in this case is 6.30. Once again, because I've rejected null here, I'm going to say comma p less than 0.05. So remember, we still had one comparison that we've skipped so far, which is the comparison, the main effect for pet gender. So that's going to be my last sentence. However, pet gender alone had no significant effects on an owner's level of happiness, comma F, degrees of freedom go in the parentheses. This time it's going to be 1,84 equal to my F computed value of 1.40. Because I have failed to reject the null, this is going to be followed by p is greater than 0.05. So essentially this conclusion is showing me that pet type alone and the interaction of pet type and pet gender have a significant difference, have a significant effect on an owner's level of happiness. But if we consider just pet gender alone, that actually did not change an owner's level of happiness. So an owner doesn't feel more or less happy if their pet is male or female, but they may feel less happy or more happy if the pet gender is paired with the type of pet they have. For example, a squirrel, a bird, or a bunny. So hopefully that gives you a better idea of the concepts and how to calculate a two-way ANOVA. Again, it's really an extension of the one-way ANOVA. So if you are still struggling with understanding what the different variances are, the different sources of variance, go ahead and review the first video on one-way ANOVA and then come back and revisit this one. Otherwise, I hope this was helpful for you. I hope that you are able to craft your own research projects and research questions, and hopefully that you will be using something more intricate than a t-test. For example, this two-way ANOVA, aka factorial design. As always, thank you so very much for watching, and I look forward to seeing you once upon a dream, or actually right here on Once Upon a Lecture. Bye!